My name's Joey. I'm a PhD student at the University of Pennsylvania in computer science, and I sort of wear two hats. So I work in a neuroscience lab, but also in a computer science lab. On the neuroscience side, the lab I work in is with Conrad Cording. So he's kind of like has his hands in a few buckets, but he's a computational neuroscientist. He likes to use math and statistics to try and analyze what brains are doing, but he's also kind of philosophically inclined. So he has his ears turned towards fundamental problems as well. So everyone in the lab actually works on quite different things, but everybody I think is unified in also having their ears turned towards fundamental problems in the field. And on the computer science side, I work with Steve Zdanjewicz and the programming language group at Penn. And he works on compilers. So he thinks a lot about how to prove that compilers are translating programs to new programming languages or to hardware correctly in a way that doesn't sort of corrupt their meaning. And what I'm doing with both of them is sort of trying to find programming languages that might have an implementation in brains, brains with a humongous asterisk, because there are a lot of idealizations I make in my work, as in this talk. And I should also say that this is work that I've been doing with someone named Nada Amin at Harvard as well. And sort of loosely, there are some threads of even Dan's thinking from conversations I've had with him over the years that show up through this talk. So I'm grateful also to be invited to talk here. It's my first time talking at MetaUni, which is a super cool venue. So I'm really excited. So to get things started, the title of the talk is "When Do Neurons Represent True?" Now, I'm not really only interested in when neurons represent true. In reality, I'm interested in when they represent anything, like a face, or how a monkey might jump, or even how I'm representing the Roblox avatar on my screen right now. But that's really hard. So instead, I make some idealizations, some simplifications to the problem that I think still help us get a grapple on what's hard about this problem. And the reason why this problem is interesting, because it might not be obvious why this is interesting, why would you want to know when neurons represent anything, is I think for the same reasons why you might want to know how your CPU is representing Roblox right now. So in virtue of being here and seeing the talk, it's a certainty that whatever computing device you're using is representing Roblox. And because of that, there's a lot that we can actually do. So suppose, for example, my avatar had 50 legs, not by design, but by accident, some weird fluke of programming. Then because we know how Roblox is being represented in your CPU, we can actually change the representation so that my avatar has 2 legs as desired. And for similar reasons, I'm interested in being able to identify what neurons are actually doing or what they're representing for cases of when things go wrong, say when there's brain trauma and you can no longer represent, say, your ability to walk, despite having sort of fully functioning legs. Now, this is stuff that I don't think is going to happen in our lifetime, but there's a lot of progress I think we can make in just developing the right theoretical lens on the problem, even in quite simple settings. So that's why I find it interesting. And I thought maybe we should start with the typical answer that neuroscience might give to the problem. I'll stop again and say if there are any questions at any point, please just squeal, scream, or say words. But what I did was I just queried a few of my friends at various stages, so like postdocs or new grad students, senior grad students, and I asked them, how would you answer this question of when a neuron represents anything? And almost all of them at first were just like, I need some more clarification. So they were a bit thrown off by me asking when they represent true, because that is a bit of an unorthodox piece of data for a neuroscientist to think about. So the question most of them actually ended up answering was, when do neurons represent X, where X is like whatever you want it to be. And I'm going to try to summarize in words on the left-hand side what these responses were, And then on the right, I'm going to try to really, really compress the essence of what these answers were getting at. So on the left, the first response says something like, neurons represent things when, or particular behaviors, when those neurons sort of fire a lot, or they become hyperactive with the onset of that activity. So you could imagine maybe we're all observing like a monkey with a helmet on, and this helmet is collecting data from its brain. And what you might notice when looking at this data is that there's some region of the monkey's brain that sort of goes crazy. The neurons start firing like crazy when it starts hopping. And what response 1 says is that you'd be inclined to say that those neurons that are firing like crazy when the monkey hops are representing monkey hopping. And it turns out to be some kind of like correlational argument that, it tends to be the case that when monkeys hop, this part of the brain tends to fire a lot faster versus when it's not hopping. So that's the first response. The second response is it's a bit different than the first one, but the important part that it mentions is about the marker of the representation being invariant to a sort of a cross context. So to keep up with the monkey hopping analogy, what response 2 is suggesting is that something's really a representation when you can find that signal, find that hyperactivity in that brain area across context. So if the monkey is hopping in Brazil or in a dark lit room or in a classroom, it should still be the case that from the helmet it's wearing, you can find the hyperactivity in that same region of the brain. It sort of helps convince you that you're really identifying something about monkey hopping and maybe not something about the external environment that it's in. For the third response, it's pretty similar to the first one. It just adds an extra condition that says that if you found something that you think is a representation, you should be able to also find evidence of it being used elsewhere in the brain. So maybe the relevant analogy here is a program. So if you have a representation of a list in some program, almost certainly you're going to be doing something with that list elsewhere in the program. And just as you should be able to find elsewhere in the program evidence that this representation of a list is being used, you should also be able to find evidence in the brain where this representation is being used elsewhere. And so kind of grossly summarizing these perspectives, on the left, I've tried to come up with like a 3-step approach to how maybe 80% of neuroscientists would answer the question of when neurons represent things. There's perhaps a step 4 and a step 5 missing, but what's important about these 3 steps is that I think that they are fundamental. So the main disagreements people would have are probably with whether or not there should be extra steps to the 3. But the basic 3 that I identify here are fundamental and also help me highlight where I think there are some gaps where we can improve the 3-step answer to the question. So step 1 is always going to be whether or not you, whether it's true or whether it's monkey hopping or whatever, whatever you're trying to find or identify in the brain, you need to render it as a vector. And the reason why is because almost always when we record data from the brain, we render that data as a vector. And so in order to be able to make comparisons between that data and what we are ultimately interested in, either monkey hopping or whatever, we need to render it in a common format. So step 1, you have to take the thing you care about and map it to a vector. How exactly we do that is actually going to be a bit of the core content of the talk later. But for now, don't worry about it. Just assume you have some means of getting a vector out of the thing you care about. In step 2, you have to make some recordings from the brain. There's a lot of nuance in figuring out where exactly in the brain you want to collect data. But once you do, you can move to step 3, where by virtue of some clever statistics, you can compute some kind of correlational measure between the description of, say, monkey hopping or true as a vector and some region of the brain's activity as a vector. And just to give a brief intuition about maybe what these numbers mean, When you see a vector with like a bigger number, it suggests that maybe there's a neuron that's firing more often in some like half-second time window, something like this. But when you see a bigger number, you should just think like more activity, lower number, less activity. Let me move this guy. And then I want to also highlight in this three-step process that it's not just some kind of like spurious correlation finding activity, but that these three steps have actually been quite fruitful. So I want to shift your attention to the slide on the right now. And also to a sort of famous case study in neuroscience, a success story really, and how this three-step approach has actually helped us learn some interesting things about the brain. So the question now is, when do neurons represent faces? And the first step is that you have to take a face, or rather an image of a face, and render it as a vector. Thankfully, we know how to represent images as vectors. There's a quite natural interpretation of images as vectors, where the numbers and each entry represents sort of a pixel value, or the strength of a pixel value. For step two, it's a little bit trickier. We sort of historically didn't always know where to look for in the brain for neurons that sort of care or become hyperactive towards face-like images. But to make a long story short, if you look at the red highlighted regions on the right-hand side of the slide, the red highlighted regions are the FFA, a part of the brain where it pretty reliably exhibits hyperactivity whenever you look at a face object versus a non-face object. And if you render those descriptions of, or render that neural activity rather, as a vector, you can do some kind of clever statistics and show that there's a strong correlation between the description of a face as a vector and the neural activity in the FFA as a vector, which hints at the fact that the FFA is representing faces. It turns out not to just be a correlational argument. There's a pretty insane, a variety of like insane evidence that also backs up the idea that the FFA does face-like processing. This is a bit of a digression, but it's just too insane not to mention. There's a cool study that someone did where there were these patients, I think in Japan, that had a severe case of epilepsy. And for severe cases of epilepsy, usually how it manifests neurologically is that there's some small part of your brain that's firing like obscenely too fast. And so for extreme cases of epilepsy, that region is usually quite small. And the way you treat it is by finding where the hyperactivity is and then resecting or removing that piece of the brain. So there was a patient that had, for which they were trying to localize where the epileptic seizures were originating from. And they had electrodes planted directly on like tissue, like neural tissue on the brain around the FFA. And the doctors basically called up Nancy Kenwisher, who's like a neuroscientist that helped identify the FFA as a face processing region. They contacted her and said like, hey, look, we have electrodes on this patient and the FFA. Essentially, do you want us to try to like stimulate that area of the brain and see what happens? Of course, with the consent of the patient. And they did do this. The patient consented. And they have these insane videos of this patient looking at a bunch of like ordinary objects like basketballs or like a vase. And the moment that they stimulate the FFA, the patient starts like hallucinating faces. All of this to say that the three-step approach towards identifying how neurons represent things isn't just like a silly correlational activity, because you can find spurious correlations in a lot of things, but rather it actually has helped us identify some oddities about what brains are doing. Now to the elephant. So there's a big but here. So it's not all a magic success story. The elephant in the room is really has to do with step one, and I'll elaborate what I mean by that. So I'm going to go through the kind of original example again and highlight a way in which you might actually misjudge neurons as not representing when they could be. And that's the elephant that I'm going to try to kind of continue to point out throughout the talk, which is that we might have the means to measure and record from the right neurons and do the right statistics, and yet still not notice that the representations are sort of hidden in plain sight. So the first step is, again, map the thing to a vector. Step 2, we're collecting data from some new set of neurons. We have a 4-dimensional vector instead of a 2-dimensional vector. And then you compute some correlational measure. And in this case, the measure is low, so the typical neuroscientist would say, oh, it's probably not representing true. The problem is that depending on how we choose this map from true to a vector in step 1, we might actually be able to get a strong correlational measure. And that's what's happening here on the right-hand side. So supposing that you can map true to this vector on the in step 1, and using the same exact vector description of the neural activity, in step 3, you get quite a high correlation, which begs the question of how do we know what are the reasonable mappings to consider in step 1, right? Because depending on how I choose to map the thing I care about, either monkey hopping or true or faces to a vector, it can impact whether or not I diagnose the neurons as representing the thing I care about or not. And this is a big problem. Like, this is to me probably one of the most fundamental problems in neuroscience. And I'm not unique in making this observation. There's this paper now, if you turn your attention to the right-hand slide, there's this paper called The Maps Problem and the Mapping Problem. And it's by David Popel at NYU. It came out about 10 years ago. And what he's pointing out in this paper is that he's interested in language. So if you read a paper by someone that studies language, the things they like to talk about are kind of discrete entities like verbs and noun phrases, or the rules that children use to conjugate the verbs or come up with the past tense of verbs, things like this. And what David points out in the paper is that we have no idea how to map these kinds of descriptions of language to the brain. And to quote from the paper and summarize it in one sentence, he says there's really no mapping to date that we understand in even the most vague sense. And the mapping that he's talking about is really the same mapping that I was just discussing in step 1 in the slide on the left. Now, he's not talking about Boolean values like true and false. He cares about things like verbs and the rules implicated in language production. But it's still fundamentally the same problem, which is we have some stuff we want to describe and that we care about, in this case language, and we need to describe it as a vector. But it's not clear we have any good sense on which mappings to rule out and which mappings to strongly consider.
Am I accurate in saying that it's also a problem that there isn't a single mapping? I mean, if you're reading from these neuropixels or whatever, the representation of true, even if you could identify it accurately, it might be different in 2 weeks or something, right?
Yes, I was actually at a talk. I was listening to a talk by someone. They used to be faculty at the University of California, San Francisco. They now work in the startup space in brain-machine interfacing. And he basically just gave a half-hour talk on all the major problems with doing brain-computer interfacing. And one of them was, he said, representational drift, which is what you're pointing out. You might have, and maybe some of you actually saw this demo that was going around from Elon Musk's, I think it's Neuralink maybe. They had this demo of a monkey controlling basically a cursor, or maybe playing Pong or something, using its mind. But the crucial thing they don't show in that video is that it probably doesn't work after 2 days, because whatever signal they're tapping into to control the cursor is these will change. The nature of the vectors that you record from change so frequently. It's not static. So
why do you believe it exists?
Yeah, all this to say, yeah, you're completely right. Well, there might be multiple. I don't know if there's a single one that I'm advocating for, but I think that there are a set of mappings, reasonable mappings. Yeah. Yeah, I mean, I'm happy to be like a pluralist on which vectors should count. I just don't think I mean, clearly not any vector should count for what you can map it to, but that there should be options. And under a variety of constraints that brains are subject to, maybe it chooses one over another. But yeah, I'm not advocating that there will be like one vector to rule them all for true. There might be a collection. It might be that if you have 4 neurons in a circuit, there's a particular way to represent true, but if you have 8 that are available, you might actually be able to represent true in a sort of comparable but different and useful way.
I'm going to ask a question which skips ahead a bit, so forgive me, but I mean, you want to believe in a kind of coherent mapping of many different things to vectors that are sort of internally consistent. And if they're all subject to drift, isn't that a big hypothesis that it's all coherently drifting somehow? Isn't that signature of like some kind of symmetry that should have been noticed by now? It seems like you're asking a lot for it all to both be able to drift, but somehow drift coherently.
So this is a comment about like the mapping, whatever mapping I have from true should also be sort of registering the drift, and somehow, like so far I'm just talking about sort of simple functions, right? There's no talk about like how the function will change over time, right?
But I know you believe in more than what you say on these slides, right? So you believe in much more mapping to vectors and some internal consistency among those mappings. But that seems like if there's one mapping, then maybe it's possible to get all that right. But if every part of it is somehow drifting, how can it stay internally consistent and have the ingredients be able to drift?
I guess I don't have a good answer to it. I mean, the question of how, I mean, this is also like the focus of even people that don't even think about the step 1 mapping problem. Like there is this mystery, which is that it feels like when you record from, I mean, it's not even just what you feel like, it's what we know, is when you record from the brain, the signals are constantly changing, but still we have the percept, like I know there must be some consistency, some kind of thing that is there and invariant across time. Like I've had representations of like chairs in my brain now for I mean at least like 20 years. And there's something about the representation that changes for sure, because I've gotten exposed to more chairs in my life. I've broadened my horizons on what chairs are. But there's at the same time some amount of some aspect of the representation we think should be invariant, because there's a lot of what I understand about chairs that really hasn't changed in 20 years. I can sit on them. They usually have legs, things like this, right? So exactly how to deal with the fact that when you look at brains, everything seems to constantly be changing, but that there also still seem to be cognitively some things that are invariant across time. It's like it's a hard observation to reconcile, to deal with, really. So I think for now, I kind of get away with this by just idealizing myself to the setting where you don't have to worry about it. But it's definitely an interesting and like difficult observation to handle. Cool. I guess for me, I'd say in the shorter term, I'd be happy if I could deal with the mapping problem, even just like artificial neural networks, where you don't deal with at least where you can set up the problem so that you don't need to deal with this kind of representational drift over time.
I'll let you continue, but I have more questions about that at some time.
Yeah, no problem. So yeah, this mapping problem, which is again, how do I take the thing I care about, be it true or monkey hopping, faces, whatever, and how do I render it as a vector so that I can actually sort of play the neuroscience game? It's something that, at least according to David, that we have very little understanding of. And the way I try to operationalize his frustration is in the following questions. I think David would say that what we don't have are answers to these 2 points, which is what properties should the mapping obey? So there are clearly some degenerate mappings. Like if I mapped every observation in linguistics to the zero vector, that would be a little uninteresting. But it's at the same time not totally obvious then what reasonable constraints should we put on these mappings. And two, which should the domain of the map be? So the sort of Boolean set true false is like clearly not interesting enough to capture all the interesting aspects of linguistics and cognitive science that we want to map from. So if not that set, then what exactly should we be mapping from? And at this point, I kind of take a cue from Robin Milner. So there's a beautiful picture of Robin Milner here before I realized the censorship settings on Roblox. But no, you can replace.
You can put your head there.
Yeah, I can put my head here. Yeah.
Roblox man, Turing Award winner.
Robin Milner. Yeah. So he got the Turing Award in 1991. Actually, for a bunch of things I'm not even going to talk about. But funny enough, in the footnote of his Turing Award citation, they mentioned some of the work that he did on something called full abstraction. So he was interested in programming language semantics, and more generally formal reasoning about programs. And in programming language semantics, the game, at least the game he was playing, was you have a programming language and you want to know the meaning of each program in a really concrete, formal way. And what you can do is design a map from each program to some mathematical object that you have a good grasp over. For example, this is not what he was doing, but for the case of just as an analogy or a case study, you could think that maybe he's interested in mapping programs to vectors. And he runs into a very similar problem that we were just discussing, which is that it's clear that some mappings just suck. Like if I mapped every Python program to the zero vector, what it implies is that every Python program has the same meaning. And so you don't want to, you want to figure out what properties of the mapping should hold. So you end up finding mappings that actually genuinely capture the meanings of programs. And the answer that he came up with in the context of programming language semantics was this notion called full abstraction. And what I am trying to show in my research is that this offers a solution, or at least a method for approaching the mapping problem that you encounter in step one of playing neuroscience, the game. And for, I guess I should also say that I think that it offers two sort of direct answers to the concerns brought up by David Poppel in his paper on the mapping problem, which is that the properties the mapping should have is that it should be fully abstract, which I'll talk about shortly. And two, that the domain of this map should actually be a programming language, which I'll also motivate, because it's not obvious that you can express all the interesting things of cognitive science in a programming language. So full abstraction is this property that at least warranted a footnote in the Turing Award citation. So what exactly is this property? So full abstraction, one way to phrase
Sorry to
it
interrupt,
that
Joey. Can I just
go ahead?
Can I just clarify that we sort of have in mind two mappings here, right? One is from some kind of programming language to vectors, maybe, and another is a mapping from, I don't know, activations in real neurons also to vectors. And is that right? I mean, there's two separate mapping problems in some sense.
Yes. So you're saying in like step two, there's like you go the recordings to the actual vector that you end up with that like let's say it describes all the data you collected, the raw data.
Right, and it seems like you want those two mappings to somehow line up or something. But the second mapping problem is also highly non-trivial, because you're mapping presumably from a very high dimensional thing. I mean, you're not going to have any similarity between the vector of all activations of every neuron in your brain with anything you get out of this denotational idea, I guess. Is that right? Yeah.
So So yeah, one could say that instead of giving a version of this talk because essentially what this talk is there's 3 steps to doing neuroscience. Step 1 has some really thorny issues. Maybe the suggestion is, look, step 2 also has thorny issues. And there could have been a talk on step 2. I think that's totally true. The reason why I focus on step 1 is that I think actually that there are settings now in neuroscience where we're really not bottlenecked by our understandings of step 2 and step 3. So we have the right statistics, and we if you study small enough brains, for example, some of these issues of like how to do step 2 correctly kind of go away. I'm thinking of people studying like these microscopic worms. And what's turning out to be quite challenging is, even in the case of very simple organisms where we're not bottlenecked by statistics or our ability to measure things from brains or describe them correctly as vectors, it seems like we still don't quite have a grasp on step 1. So to me, it's true that step 2 and 3 have tons of PhDs left of juice left to squeeze. But it seems like the more fundamental problem to me is that I'm worried about the case where that is already here for simple enough organisms, where we know how to do the stats and we know how to accurately describe the data we're collecting from brains, but we don't know how to see true as a vector, right? It could be the case, to put a ridiculous example, it could be the case that like microscopic worms are representing Roblox, but we just actually don't know how to make that a coherent statement to actually test, right? It's like the kinds of things we know how to test, and this is no accident. Like the thing we understand best in neuroscience is vision. And the reason is because step 1 is most obvious when you do vision, because images require it was not obvious at the time, but it turns out that the natural notion of representing images as a vector turns out to be useful for doing the 3-step game. But when you go beyond vision into more abstract things like Roblox, it's just like we don't even know how to begin thinking about the problem, which is kind of what David Popel talks about. So long-winded way of saying, yes, step 2 should also deserve a talk, but I do really think step 1 has more fundamental problems that have yet to be addressed.
Yeah, I'm convinced. Thanks.
Yeah, no problem. So yeah, a fully abstract map, to put it simply, would be that it's a map that preserves equivalences and distinctions. So there's an asterisk here, which is that you have to pick some notion of equivalence in your domain, in your codomain, where you're mapping from and where you're mapping to. And you have to sort of use the definition in good faith. So you can always pick, you can sort of cheat and pick notions of equivalence that help you trivially satisfy this. But the silver lining here is that, especially in the context of programming languages, there are sort of notions of equivalence that are, depending on your use case, the more right one to use. And in that case, for the notions of equivalence that often come up in programming languages, it's actually quite hard to satisfy this property. And just as an example, so you kind of get some sort of mechanistic understanding of how these maps work, I have on the bottom an example of a fully abstract map. So if you take that on the set to the left, the notion of equivalence is equality, and likewise on the set on the right, the notion of equivalence is equality, then this would count as a fully abstract map, because true and false are not equal, and after you map them, they're still not equal. Likewise, true is equal to itself, and after you map it, it's still equal to itself. Similar thing for false. And just as a counterexample, so you see what happens when things go wrong, if you mapped both true and false to the, and just look at the bottom half of the slide. So if you map to both of them to the 0 vector, then true is not equal to false, but now the thing that they map to are equal to each other, which would violate the property. And as a higher level intuition about why full abstraction is interesting, usually a failure to satisfy full abstraction means that your map has either introduced or destroyed some information you care about. And usually the information you care about, or not usually, I mean, the information you care about is encapsulated in the notion of equivalence you pick. But important thing is basically, if you don't satisfy full abstraction, you're introducing or destroying some information, depending on how there's 2 ways to violate full abstraction. So this is the first kind of piece of guidance that we got from Milner on his work in programming language semantics that I'm trying to use to approach the mapping problem. But there's also the second bit, which is the domain of the map should be a programming language. So Milner was mapping from programming languages to mathematical spaces. And I think we should also be thinking about doing this in neuroscience, but from programming languages to vector spaces. And it's not obvious that programming languages are the right tool or the right language to be describing cognitive science. But before I started my PhD, I actually used to be a more proper cognitive scientist, which is how I stumbled on some of these ideas. I don't know if the rain was cueing sadness for me leaving cognitive science. Or,
no, our weather control system is broken.
No worries. But it turns out actually in cognitive science, a lot of people, and for a very long time, people have taken seriously the idea that the way human behavior is mediated is by programs being shuffled around in the head. And in recent years, people have taken what was at first a bit of just like a metaphor, like more seriously. It's kind of hard to see the image on the right, which is my fault, but it comes from a paper from people trying to make sense of how children acquire knowledge of numbers. So this is approximately correct, but I sometimes forget the finer details of the paper. But I think they're looking at data from children between ages like 1 to 4. And it turns out that children go through a few interesting stages in how they actually make sense of the natural numbers. Just to explain, I guess, a little bit of the study, first, and I guess I'm hedging just a little bit here because there's some controversy on the extent to which this is true, but at least one version of stories that many people put forth is that as children acquire knowledge of numbers, they first progress through a one-knower stage where they sort of know what 1 means, but not anything else. So 2, 3, 4 basically are uniform, like have a uniform meaning. But after being a one-knower, they become a two-knower where they know what 1 and 2 mean. And then 3, 4, 5, everything else has a uniform meaning. And the story sort of continues until they sort of sporadically acquire knowledge of the number line. They like sort of get the intuition that every number has a successor. What's important, the detail that's important with respect to this talk is that in this paper, what they do is they describe the different stages of knowledge that the child has about numbers in the form of a program. So being a one-knower, knowing what 1 is characterized by what's essentially like a Lisp or a scheme program. And likewise for two-knowers and so forth. And this isn't just like a special weird instance in one like corner of cognitive science, but actually in a variety of areas. So in say perception, so like object recognition or the perception of sound. I used to work in planning and sort of the cognitive science of planning. So I would describe people's goals and how they move in environments using explicit programs. And all of this is just to say that there's a substantial chunk of cognitive science that takes very seriously the idea that there's a sort of programming language in the mind, and that the goal of cognitive science is to identify what this programming language is and what its programs are.
This example is really interesting. Is the transition between these different programs kind of smooth, or is it sudden, like a phase transition? Or is that outside the scope of the experiments?
No, this is also, first let me find my character again. Okay, here we are. No, you've pointed out to probably what is the controversy about, not just for this example, but in developmental psychology, there's a huge divide between people who believe in like smoother phase transitions and people that believe in like bigger discontinuities. So in this paper, it's sort of putting forth a story of stark discontinuity, and where the stark discontinuity happens is children are, according to this interpretation of the data, they're one-knowers, they're two-knowers, then they're three-knowers, where they know 1, 2, 3, but everything else is uniform. And then after that, they sort of become the what's called CP knowers. So they just sort of know they sort of get numbers, how numbers work. Now, other people would argue that it's not quite that clean or that discontinuous of a jump, but that really children are like 1 knowers, 2 knowers, 3 knowers, and it goes up to like 10, and it's like it's not super clean, but this is like a major difference in how people interpret. I mean, if you're curious, this is the sort of Harvard School of Developmental Psychology is a big proponent of this kind of story for how conceptual development occurs more generally in children. And then sort of counter to this is Jay McClelland at Stanford has a paper on not just number acquisition, but other things as well, where he espouses like a more fuzzier description of conceptual change in children. That also was, okay, in a past life, I was a PhD admitted to be a developmental psychologist. So this used to be my domain. I find it very fascinating. Yeah, yeah, I was going to do sort of like computational stuff with developmental psychology, but then I started noticing the early issues on the mapping problem that seemed to captivate my brain.
I'll just comment that this kind of phase transition is in the situation of learning programs is exactly what we've been studying from the point of view of singular learning theory. So I will follow this up with you at some point.
Oh yeah. I would love to chat about it. So now there's another elephant, but a smaller elephant, because I hopefully made some progress on dealing with the elephant in the room, but it's still there. And the reason is because while Milner provides, I think, a blueprint for how to deal with some of the mapping problem, I think that he doesn't tell us which programming language to use. That's one thing for the mapping. So a programming language sufficiently expressive enough to talk about the things that the programs that cognitive scientists care about, but also he doesn't give us the mapping. And so that's basically the role of my work, which is under construction, as you can see. So what I spend my time doing is trying to identify programming languages and possible maps of those programming languages to vectors, such that the mapping is fully abstract, or at the very least some kind of weaker variant of being fully abstract. And I could talk during the question phase. Oh, actually, I'm going over time, so I'll wrap up here. I think I'm basically at the end. But yeah, I'm happy to take questions about why exactly this is difficult, why it's taking me so long, and other more broad questions about neuroscience or cognitive science. And this last slide basically just recapitulates the original slide, but where I augment step 1 to be sort of my idea on the problem, on how I would address step 1, which is describe the thing you care about, but using a fully abstract map. And that's basically it. So happy to take questions.
Thanks a lot, Joey.
For listening.
I'll just note, those of you in OrbCam, you'll have to get out and walk around a bit to find us if you want to ask a question. I have some questions, but
Dan,
given
yourself are quite quiet because you're far away from the orb right now.
Oh, thank you. Yeah, I should take my own advice. Thank you. Everybody else is already here. Okay. Yeah, given that there's not much time left, I'll invite some questions from other people, and including more broad questions, right? Just about neuroscience in general and the role of why it's even not crazy to think about logic in this context and so on.
Yeah, I'm a bit behind here. So let's take the example from the beginning. Like if I want to map the face to a vector, you're suggesting I first map it to a language itself, or like a program written from the language and then to a vector?
Yeah, according to what I said in the talk, that's completely accurate takeaway. I guess I should preface by saying for faces, I'm not actually, I think what we currently do is fine. You don't need to map it to a program and then do a vector thing. I'm more concerned with like really abstract data, like in this case, just Boolean data, where we actually just don't know how to look for the full space of mappings. Images are a little bit weird because it's not super clear like what the programmatic description of an image is, right? Like other than literally the matrix that represents that image. So I'd say that my story, I'm less interested in, like I put it this way, I'm quite satisfied with the 3-step process for perception, but I'm less satisfied with the 3-step process for studying things like language. And when you're thinking about things like language and not like images, things that we do know how to describe very well in step 1, that's where we really need better ideas. So I find my solution to be useful when you're concerned with things like the language guy from earlier, David Popple, where he says like we have no idea how to take that and turn it into a vector.
Got it.
Yeah.
I think I have a more basic question. I might have missed this right at the start. When you say you're looking for true in this particular case, are you talking about like truth as in like the abstract concept of like a true belief? Or are you talking about logical true, like when someone is doing a logic problem and they see trues and falses in on that piece of paper? Or are you talking about something in between or something else entirely?
Yeah, I think I think what you just mentioned, like true in the logical sense, you have like true and false, and there's some relations that hold and operations you can do on them, like and or not, this kind of thing.
Yeah. Interesting. Thanks.
Yeah, the idea of like what is the description of a true belief as a vector is also fascinating, but in the realm of like those things that are way too hard to think about that I feel like I'd make no progress.
Well, I wonder how did you come to choose true and like in particular this kind of logical domain as opposed to something like oneness or oneness, but like the number one, like you were already talking about some work on that concept.
Yeah. I'm also interested actually in how I could have given a version of, and I have in the past written draft slides for a talk, which is like, when do neurons represent 2, like the number 2? It just turns out that, well, there's 2 advantages. One, the representation of Boolean data in a programming language is a bit simpler. You need like less machinery to pull it off than the natural numbers. So there's like a technical reason. The second reason is maybe like to ease the burden of communication. So it's fairly obvious that true is like a somewhat abstract piece of data, but when you write the number 2, I think people just have a tendency to think that it's like more obvious how to map it to a vector. So it's just my experience and sort of finding a good motivating example. I think that true is sort of like very simple, but then there's also technically it's easier to represent than natural numbers in a programming language.
Okay, I quite like that justification. Thanks.
Yeah.
As a computer scientist, I guess I'll ask why true and not false, because 0 comes before 1.
I don't know. Maybe I could have done false. There's no special reason. I think it was a bit of RNG in my brain. I had a representation of
Matt's
the choice.
A pessimist.
That's one definition of a pessimist, I guess. The default Boolean value.
Yeah.
Why linear logic?
It's the only place where I found any guidance on coming up with mappings from like let's say sufficiently cognitive looking things to vectors. But I'm quite, like I sort of ended up in the type theory PL space, not by like sort of by necessity. I kind of got interested in it because it looked like there were tools there to help you think about these problems, but I'd be very happy to learn about other ways to approach the problem. I mean, I think the other advantage, though, of this field is that it's had the luxury of working in a much more simple setting. So, for example, like Robin Milner's work although extremely technical and profound, right? He got a Turing Award, is a lot easier than doing neuroscience. And with that luxury, he's able to sort of push forward the problem-solving approach in a way that you just can't do if you're always working on the front lines in neuroscience. So I also do think like PL has some very, very serious insights on this problem. I sometimes describe it as like, I think PL's like 50, 60 years ahead, or maybe even 100 years ahead, right? Like of like neuroscience and the way that it talks and thinks about computation. It's just that neuroscience is burdened by having to be on the front lines of the fight and actually trying to describe real neural data, right?
We're going to move over to
linear logic. I can use it now, but yeah.
Yeah, makes sense. Thanks a lot, Joey. I got a lot out of that. Would you be willing to come back and talk a little bit more about some of this in one of the other seminars at some point?
Oh yeah, for sure. 100%. Especially now that I have Roblox downloaded. So.
Yeah, it's interesting you talk about this this drift problem. I mean, that reminds me of. I mean, there's the emergence of representation theory in physics, which is to some degree what Russell's going to talk about in the next session. Is to do with the realization that there are many ways in which when you measure the world, your measurements might change, but the underlying thing is really the same, right? So, for example, if you are taking measurements of an electron from different points of view, you might represent it as a different quantum state, but they're really the same thing you're measuring. And representations of groups entered physics directly as a way of formalizing that observation. So it does... it makes one wonder what one uses the term representation in machine learning and neuroscience in a very different way to how mathematicians use it. But maybe they're not so different after all. That wouldn't be so surprising. So yeah, I wonder if there are...
No, for sure. It's. This is relevant to your point about step 2, right?
Yeah, that's right.
From earlier.
So, yeah, it would be interesting to know more about the nature of this drift. It seems kind of fundamental rather than a nuisance.
Oh yeah, for sure. Especially if you want to actually do anything. The brain.
I want to ask a question about transformer models. I mean, I know people have done neuroscience work where they look at people reading text and try and decode that using transformers, and they make some statements that the brain is like a transformer, or at least the representations are similar. I have to be honest, when I see such papers, my immediate thought is that it's bullshit, but you would have a more developed take on that.
I think Conrad would be inclined to agree. I should say I think so as well. Some of my friends actually are sort of in this enterprise in neuroscience. They kind of take big neural networks and I think that initially the success story was in vision. So when the ImageNet moment happened, like almost immediately around like 2012, neuroscientists were like, wow, these things are getting kind of good at object classification. Why don't we try to sort of get a monkey to do the same object classification task and then see if there's like a way to predict neural activity from this, like basically from like AlexNet or something. And what you find is that you can do it, and you can do it better than any other model in neuroscience. And now people are trying to do that with language. So I have some friends that maybe it's the study you've seen. But it's funny talking to them actually, because everybody's like all over the fence on it. I think your gut reaction is not too extreme. Like a lot of people really don't know what to make of these studies, where like, let's say you're measuring neurons from someone's brain as they do a kind of next word prediction task, and then you have GPT-3 or whatever do the same next word prediction task. You can probably, and I mean, this is what they show. You can sort of get state-of-the-art like prediction of the person's like brain activity by using the sort of weights for the activity in GPT-3 or whatever the large language model is. I'm with you though. I don't really know what to make of the studies. They're provocative and contemporary discussion has not resolved the debate.
Yeah, I guess from your point of view, it's maybe not super relevant, but there's an angle on that I think is highly relevant to what you're doing, which is, okay, maybe they're not that similar, perhaps, but they're both learning machines and they both have some similarities. Why not take a synthetic view of trying to find these mappings you're talking about just in GPT-3? Forget about the brain. And if you can find, if you can't find it there when you have access to everything, then the prospects of finding it in a brain seem more remote. Isn't that a good synthetic test?
Yes, that's exactly why I'm in a computer science department and not a neuroscience department. For exactly that reason. I think that we can develop a lot of the tools you'd need, at least for me, for what I want to do, much easier in a computer science department.
Yeah. All right, let's all thank Joey.
Thanks, Joey.
Thanks for listening.